this lecture, and Bill is going to take forward. So what we intend to do today is do a little review and prove some theorems and give some concrete examples. So we will look at the equivalence problem for the affine group online, and we look at extreme value distributions, generalized Pareto distributions, and Bill is going to do the proof of the duality of domains of attraction. We showed that in Cartan's method for equivalence class, distribution under the affine transformation group was determined by a functional relation between two invariants I and J, where if you take a distribution, you write it as log of distribution is the I, and J is going to have that relationship. You can see that second order differential equations are going to be involved in this. You have a second derivative here. We showed that the efficient chip stability conditional is really given by this equality, the class of equivalence of powers satisfied by that invariant relationship. And we show the stable distributions that can be written in that form, or the alpha determines if it's going to be a Weibel type, a Fisher type, or a Gumbel, which is Bill's going to show that this condition IF is equal to 1 plus alpha is necessary and sufficient. And I'm going to start by showing some examples of the convergence in some concrete case by using nonlinear regression. Nonlinear regression is not as standard as linear regression. You have a simple form, but there's lots of implementation. And we look at the Maple implementation because historical reasons is the software we're more acquainted to, and some Python implementations, and we found that the results are coherent. This is an example of work we did on virus, where we took data and we did use Python to do a nonlinear fit with a Gompers curve. A Gompers curve is just a multiple of a Gumbel distribution. Why we were looking at that? Because Michael Levitt, in the beginning of the COVID crisis, said they follow Gompers curves. And the thing he got mistaken was to imagine that there was only one Gompers curve that would describe the virus evolution. And in fact, in the beginning of a wave, a virus wave, you change, the parameters of the Gompers change quite a lot. And once the wave is established, it has some kind of convergence. We did a long paper about that. You can find doing Cascon, Shadwick, COVID-19 search. And we haven't published in a smaller format yet. It's just, but this is one example in Brazil for COVID cases, there's weekly cases. And this is a Python fit with a Gompers dense Gumbel distribution. And you can see in the graph how good the fit in red matches the data in blue dots. And you have the parameters. And the first is the A, the second is the B, and the third is the N. That's a scalar N times the Gumbel distribution. Here I'm going to do some more examples using Maple, just in different ways, just to show you what you can do. The first, I'm going to import some data in matrix form, is the data from exponential with a grid 0.1. And I extract the points from that matrix. It's the structure of the points. To found the Gumbel that corresponds. I just used nonlinear fit. So this is the Gumbel. This is 0.1, 0.2, 0.3. And Lex is the matrix of data. And that's the result. That's the Gumbel distribution. The best approaches the data. I started in this example taking data from the beginning of my data set. So it's on the left of the exponential. And I don't imagine that the fit is going to be as good as when I take points from the right, which I'm going to do very soon. And I'm going to show the plots for both of those and the errors functions. Okay, so this is the nonlinear fit result from before. And I just copy and paste as a function, being careful because when you copy and paste, it sees that T is nothing. You have to put a multiplication sign. Maple is like that sometimes. And you see in the graph that the fit is not really excellent, definitely not. And that's the error plotted as absolute value of the integral of the difference of the integral to absolute value of the difference. It's well over 0.02 except for some points. Now, when I do the extraction of points and I guess that slide disappeared. Okay. I did the same thing. I extract the points. I did a nonlinear fit, exactly the same thing. And now I plot the result that I obtain against the exponential. And you can't see the difference. It's not visual. Okay? It's in 94th percentile. So this is I call solution 2. I can write solution in Portuguese, so Maple doesn't complain. And but now I can see the same error integral, and it's 3 orders of magnitude smaller than with the first fit. So when you got more towards the attractor, which Gumbel function is the attractor for exponential, you got a better fit. Now it's Bill. Go ahead.
So the general theme of these talks has been the geometry of probability distributions. So here we're the process of geometrizing extreme value theory. The conventional approach to that, you can look in just about any treatment of the subject, starts with the original motivation, which is looking at the distribution of largest values taken from samples of size n IID samples from a given distribution. And of course, immediately you can see that those largest values, another random variable, has to be distributed by f to the nth. So that gives us the Fisher and Tippett stability condition. They're really looking at the equivalence of nth powers to the original distribution under the affine group as n tends to infinity. And out of that, they found these 3 types of extreme value distributions. They found them as 3 quite distinct things. The variables on the domain from -infinity to 0, the Frechet's on a domain from 0 to infinity, and the Gumbel on the real line. And then a few years later, Richard von Mises showed that, well, it's actually a one-parameter family. They're all connected. And this is the modern version of the description, where you make the connection obvious by changing the domain. You have variable domains depending on alpha. And then it becomes easy using first-year calculus exponential function as a limit to see that the limiting value is the absolute value of alpha goes to infinity, is the Gumbel distribution in both cases. So we started by looking at this from Fisher and Tippett's point of view. So they're looking for a series of location scale transformations. And you'll see in the standard treatments, they'll give examples, and they'll show you what AN is and BN is to make the limiting transformation. But for this to be useful, you need to have some much more powerful way of checking whether a given distribution belongs to one of these limits or not, rather than going and looking for a series of affine transformations. Gdenko, in a paper which he discovered the limiting distributions, I think, independently of Fisher and Tippett, but also gave simple limit tests. So you just look at the tail of the distribution, take this limit that involves this shape. And when you see these things treated in the usual way, it's not usually remarked on, but it's odd, to say the least, that Gdenko's formulas make n disappear, right? This n has actually nothing to do with the test. And in Gdenko's case, the tests for Frechet and Weibel are very simple, easy to use. Gdenko himself gave several attempts at a test for necessary and sufficient conditions for the Gumbel distribution, but he says in the paper that they're not satisfactory. They're not simple. He wasn't very happy at all with what he was able to do with the Gumbel distribution. But this is the test for the Frechet distribution. It's very simple to implement. I mean, you can often do it very easily by hand, but you can certainly do it in symbolic manipulation calculations with no trouble at all. And there's a similar test for the Weibel distribution. So it's just the asymptotic shape, if you like, because you're comparing the distribution with its rescaled versions, scaled by t. And in fact, that's the reason that he had trouble with the Gumbel distribution is it's really not scalings that are responsible for the Gumbel distribution's stability, it's translations. So you take the Gumbel distribution squared, you can see that that's just the translation of a Gumbel distribution. It's not a rescaling. So then in the usual approach, there's a bit of a bait and switch because all of a sudden they start introducing generalized Pareto distributions. And they have a natural description. They come about by looking at distribution conditional on being above a certain threshold, a peak over threshold condition. But the justification for their existence is never given. And why? The property they have, namely that everything in the domain of attraction of the general of the extreme value distribution with parameter alpha is going to converge also to the generalized Pareto distribution with the same parameter. But that's actually much weaker claim than it sounds like, because everything in that domain of attraction is converging to everything else. So what is it that's so special about the generalized Pareto distributions? It isn't that just that they match up with the parameters in the extreme value distributions. You can easily check, for example, that the student T distributions line up with the Frechet distributions for alpha equals 1 to infinity. So that's not what is doing it. But in both cases, we see these problems. We start off discussing largest values in samples and how they're distributed, turning into a discussion about the tails of distributions, the asymptotic tail of the distribution. So our version of this replaces that stability condition by, we could think of as a geometric stability condition. It's just the equivalence class of any power has to be stabilized by the affine transformations. Now, if this holds, then clearly the other ones, the Fisher-Tippett one will as well. But you might think this is a much different condition, and it might give you different results. But in fact, it leads directly to the extreme value distribution. So the extreme value distributions came right out of this. Then we introduced something that's really, again, it's the mirror image, if you like, of the way the generalized Pareto distributions are introduced. It's distributions conditional on falling below a certain threshold, and that equivalence relation. But it turned out, again, that's an exceptional case for the equivalence problem. The invariant being constant is exactly what produces this stability. So that's a common feature now. So we know what's special about these distributions. They're the exceptional case given by J equals constant. And when you compute their mirror images, you end up with the generalized Pareto distribution. So in a sense, what's special about generalized Pareto is that they're mirror images of exceptional distributions for the affine equivalence. And that's also, we'll see, true about the extreme value distributions. And in both cases, because of J is just second derivative of I divided by the first derivative of I squared, the relations ij equals constant or j equals constant are second order differential equations. And that's a critical part of this. So via the geometry, we've got an explanation for the usual suspects in extreme value theory and the generalized Pareto distributions. But then there's also a geometric duality between these exceptional distributions on both sides of this, which we'll show today. So if you look at the mirror image of the extreme value distributions, they're in the domain of attraction of the j equals constants and vice versa. So this is the theorem. This is the basis of the theorem, is this calculate. This is really a calculation. You start from the definitions, the mirror image distribution, remind you, it's called that because if you start with the probability density functions, one here, then it's mirror image over here in the x-axis leads you to this formula for the cumulative g of x is 1 minus g of minus x. That's the mirror image formula. Here it's just minus, right, in the PDF. So that's the basis of the exercise, which I suggest you do. It's a simple enough calculation. So we've called this a duality of domains of attraction term, but we still need to explain what is this domain of attraction and establish that those are the limiting invariant is the condition that makes you approach the attractor. So the example that Anna did with the exponential distribution, whose attractor is the Gumbel distribution, you could have done equally well with the mirror image exponential distribution. That's just e to the x on the negative half line. And that's a j equals constant, was one of the exercises from the first lecture, I think, to say which j equals constant that corresponds to. And just as Anna showed the approach of in the tail, so above the 94th percentile, you get an incredibly good fit between the Gumbel distribution and the exponential distribution. That's because it's being attracted to the distribution. So that's what the attraction, domain of attraction actually means in practice, which you start to see through Budenko's things, but is really obscured somewhat by the usual formation of the problem. It's not a matter of finding a sequence of transformations. The fact is, what's happening is that the distribution is becoming closer and closer after a transformation, if you like, to the target distribution. Now, in the example that Anna did, because if you want to do many of these things to fit the Gumbel distribution, you want to make your starting distribution the standard one, and then find the parameters for the Gumbel distribution to the fit. Well, you can either do the affine transformation on the target or on the fit. It doesn't matter. It's the same thing. But what happened in those examples you saw was we changed the parameters. It wasn't the standard Gumbel distribution matching a transformed exponential distribution. It was transforming by an affine transformation the standard Gumbel distribution and showing that gave an extremely good fit to the exponential, the standard exponential distribution. And that fit gets better and better and better as you go through. You saw the drop of the error by 3 orders of magnitude once you got to the 94th percentile. If you go out to the 98th percentile, it will drop again precipitously. So what we're trying to get at is exactly what's going on in terms of these curves, the actual distribution itself in these domains of attraction. And what we're saying is, one, it's very easy to check whether something satisfies is attracted to an extreme value distribution. You simply compute the limit of its invariant. If its variant has the EVT constant, then you're done. There's some work to showing that that's the case, but that's the result of it. Now, of course, this is obvious in one direction. If ij has a limit for a distribution f, if that limit is 4, then there's no conceivable way we can approach an extreme value distribution that has a limit of 2 or 15. Right? There's only one possible choice. The question is whether it's really getting close to that one or not, which we'll come back to. But the fact that it's necessary is obvious. Now, the thing is, you don't have to make up some kind of exotic distribution in terms of measure theoretic this and that, for example, in order to find something that has no EVT limit. Van Mises showed that a real analytic distribution that has no limit here it is. It's real analytic. There's nothing exotic about this, except that that sign term makes it wiggle, okay? And it keeps wiggling as that x goes off to infinity. So we just really just modified the exponential distribution by adding this wiggling term, and that's enough to keep it from satisfying our necessary condition. And to see that, we just compute the graph. I mean, you could go ahead and look for an analytic proof of that. You should be able to produce one, computing the invariant. But in fact, it's easy to see what's going on as soon as you draw the graph. Very quickly settles down to periodic form. So there's clearly no limit. Now, of course, the question is what happens as x goes to infinity, and if you can read the scale on this graph, this goes all the way to x equals 30, which is a bit short of infinity. But on the other hand, by the time you get to x equals 20, f is within 1 part in 10 to the 9th of being equal to 1. So we're really, really out in the tail. All right? And by the time you get to x equals 30, this graph was drawn in Maple, which is usually pretty good, except it has an Achilles heel when it comes to exponential functions sometimes. And that inevitably shows up here. So if I tried to draw this graph to 31 instead of 30, I just produce a bunch of noise beyond this last bit. But I think it's pretty convincing that if we could draw it, we'd see the same thing repeated again and again and again. So if you really want to do an exercise in analysis, you should try to prove that that's the case. But this much of the curve we can see easily. So this really comes down to the fact that what we've got is determined by ordinary differential equations. So we saw from the very first thing when we solved the equivalence problem, the solution boiled down to the way one invariant, j, appeared as a function of I. Right? That functional relation was the remaining information. When we got to that point, we saw that the equivalence problem was solved and that the equivalence classes were given by those functional relations. But that's a second-order differential equation. Right? It looks like y double prime over y prime squared equals some function of y. That's it. And there's one for every distribution, at least every distribution that's got two continuous derivatives. So we can really, this solution of the equivalence problem is really telling us that the distribution is equivalent in a different sense. It's the same thing as this second-order differential equation. Solve this differential equation. The initial condition, the affine parameters, the A and B, the location scale parameters, are the constants of integration. That's it. That's the whole package. It's all a matter of this differential equation. So every distribution, as long as we can differentiate it twice, we can regard as the solution of this ODE. There's a unique ODE attached to it. Different H of I's are different equivalence classes. Each equivalence class is a distribution with its whole parameter range, location scale parameter range. That's it. And that's all that's there. Now, of course, if you start with an arbitrary distribution, pick one out of the blue, it's entirely likely, it's sort of a generic almost, that you won't be able to explicitly find I as a, right? What we know about J is it's a function of X. We've got it explicitly written as a function of X, but we'd have to be able to invert the equation I equals log F to get X as a function of I if we want to carry this process out explicitly. Nevertheless, we always can think of this identification of the distribution with its ordinary differential equation, even if we can't write that down explicitly. So here we're back to the exponential distribution that we saw the fit for. It's easy to check. You can actually do the inversion in this case. And you can calculate J, and then you can work out what H is as a function of I. It's just 1 over e to the I minus 1. Well, as x tends to infinity, I tends to 0. It's log of f. F's going to 1, so the log of f is going to 0. And the limit of this is 1. And it's important that you see that limit whether you calculate it in terms of x or whether you calculate it in terms of I. You can't, it's the same object. So doing the calculation these two different ways has to give you the same answer. And the limit is 1.
And this is going to be true for any, if you change the coordinates and write fx in another complicated set of coordinates, you're still going to have the same thing?
Well, as long as they're the affine coordinates. This doesn't tell us anything about what happens if we're allowing x to be an arbitrary function of x. But as long as x is just ax plus b for some other, ax bar plus b for some other x bar, then this is going to be the case. All right. So what this the exercise finishes with, showing that the limit is 1. That means the limit of the exponential functions ij is the same as the Gumbel functions ij, which is 1. Right? And that's why we saw such a good fit, because the exponential function, as you get further and further out in the tail, is getting closer and closer and closer to a Gumbel function. Not the standard one, but one that's moved by not very much. In fact, if you check, you can see that the fit between the exponential distribution and the standard Gumbel function is not bad at all, especially as x tends to infinity. And in the example that Anna had, the parameter a was close to 1. That's what was found by optimizing this, minimizing the squared errors. So if we think about the differential equation for the exponential distribution, then here it is, because the right-hand side is h as a function of I. 1 over e to the I minus 1. So what happens here as x tends to infinity? Well, as x tends to infinity, I tends to 0. Just do the power series expansion for e to the I, and you see that the limiting differential equation is the one that gave the Gumbel distribution. So this is, that's exercise 2, is to check that. Remember, the extreme value distributions are characterized by Ixx over Ix squared equals a constant over I. That's it. In the case where the constant is 1, we've got the Gumbel distribution. And that's where this differential equation is heading as x tends to infinity, as I tends to 0. And that's why the exponential distribution is getting closer and closer and closer to that Gumbel distribution as it's in the tail as you go further and further out. Because the equation that defines it is getting closer and closer to the defining equation of the Gumbel distribution. Okay. Now, the difference is the initial conditions. That's the matter of the affine transformation. Right? Those two, the initial conditions are precisely the parameters of the affine transformation. So this is all rolled up into one package through this process. Of course, without the equivalence problem, one, you don't know that j equals h of I is the way to characterize all twice differentiable distributions. There's no way to know that. You don't know that it's invariant being constant that characterizes the extreme value distributions. And so you can't observe this correspondence. Repeat, we're not looking at a coincidence here. The Gumbel distributions, the generalized Pareto distributions are good ones to do these examples with, because you can solve, well, at least using them, maybe you want to use a symbolic manipulator to do the solution, but you can actually back out the x as a function of I for those, and you can for Weibel's and Frechet distributions as well. But you can't, for example, at least Maple can't, and I can't. I'm sure there is no. I'm pretty sure there's no explicit description for the CSS distribution to solve for log of that. Solve log of that equals I for x as a function of I. I don't think that's going to happen in closed form. And the normal distribution, likewise, you don't have a simple closed form solution. So you can't necessarily see this explicitly, but you know it's there. The same argument holds, independent of whether or not you can extract an explicit form for h of I. So here's the first Frechet distribution, Frechet with parameter equal to 1. And parameter, the ij is 1 plus 1 over alpha was the parameterization we ended up with. And as the size of alpha tends to infinity, this goes to the Gumbel distribution. So this is the Frechet. It has ij equals 2, so the alpha is equal to 1. Okay. And again, we're going to look at the attractor among the generalized Pareto distribution. I was calling this G. G of x1 is the generalized Pareto distribution with the same parameter, alpha equals 1. So you can calculate jg of x. It's minus 2x minus 1. And then you need L'Hopital's rule to compute the limit of I times j as x tends to infinity. Because you've got, this is going to minus infinity, and the I is going to 0. But one application of L'Hopital's rule, and you find the limit 2. So these two things are going to the same place. What does it say about the differential equations? Well, this one's a little more complicated. But again, we can solve ig equals log of the generalized Pareto distribution to get x as a function of g. It's just e to the ig over 1 minus e to the ig. Okay. And if we substitute this into the expression for j, we get this simple looking, this is a simple function of, as a function of I, e to the I plus 1 over e to the I minus 1, e to the capital I, not the complex I. And so the product here is given in equation 15. But again, this is something you have to hope the L'Hopital's rule will give you the answer to, although you already know what it must be, because IG is going to 0, so the numerator is going to 2, but the denominator is going to 0. So, but lo and behold, plug into L'Hopital's rule, and what do you find? You find the limit of 2. Well, you have to find the limit of 2. We've already done this, right? This is just a different way of writing the limit we've already computed. But the content of this calculation we've just done, right, is to say that the differential equation, IG equals this, is tending to IG equals 2, which is precisely the equation for the Frechet distribution. That's the differential. So viewed in terms of just functions of x, this tells us what the limit of the invariant is. Viewed in terms of differential equations through inverting I equals log f to get x as a function of I, we get an interpretation of the differential equation limit. And the differential equation limit is the equation for the Frechet distribution. So the same thing happens when you look at the attractors defined by J equals constant, the things that arose from stability of distribution conditional on being below a certain threshold. You can do that in exactly the same way. You're looking at a second order differential equation. The fact that the invariant, in this case for J, is constant means that things are going to be close to that in their tails behavior are the things whose invariant has the same constant as you go to the left now. And the reason is exactly the same reason. The same equation that tells you what the invariant limit is tells you what the differential equation limit is. So there's no place to hide. Now, I mean, we can make this more precise, adding epsilons and deltas. But really, this is the essence of the proof. Right? We're going to appeal ultimately to two things. One is the existence theory for ODEs, right, where we have this very strong results of existence uniqueness and smooth dependence on initial conditions, right, for second order equations. And the other is the fact that this invariant I times j can be used to measure convergence. So if you start with suppose you start with the knowledge that the normal distribution is you compute its invariant, you find that its limit is 1. So it's in the domain of attraction of the Gumbel distribution. What exactly does it mean? What does that mean, for example, if I got my standard normal distribution, mean 0, standard deviation 1? What values of x do I need to be looking at to get close to the Gumbel distribution? I guess that, of course, the lesson here is that depends on which Gumbel distribution you're looking at, okay? Because if you change the parameters in the Gumbel distribution, you'll be looking at different values of x. And the fact is that this invariant, evaluated at quantiles, is again, that's a numerical invariant. So that's exactly the tool we want to have to measure how far we are from one of the extreme value limits. We've got an intrinsic measure of convergence. And this has very, very important statistical applications because the more rapidly convergent the distribution is to the EVT limit, the less data you need to be able to fit that limit. This is why the generalized Pareto distributions are so well beloved by the statisticians. They converge in these tails very, very quickly. The exponential distribution is the Gumbel limit analog of the extreme value distribution. You saw how quickly that converged as you went out into the tail. But this is an asymptotic result, and we have in lots of applications in finance found places where in fact there was no advantage for the generalized Paretos over other distributions. But anyway, get an example for the normal distribution, and this goes back to Fisher and Tippett's paper as well. They noticed that they called this penultimate approximation. They noticed that the normal distribution's convergence to the Gumbel distribution was incredibly slow. And this is really quite remarkable because they must have noticed this through the work of calculators, which at the time they did this meant women with adding machines. Right? Those ladies were called calculators, and they did the calculations. Right? Massive amounts of calculation, really unbelievable volume of computation that was done going into these things. But the negative values, E minus 20, that's a Weibull distribution. All of those are the 1 minus 1 over alpha. And as the alpha gets bigger and bigger and bigger in absolute value, you're getting closer and closer to the Gumbel distribution. But so you're at 0.95 with e to the minus 20, right? And there's the description in quantiles, okay, of the normal distribution convergence. And you see, it takes it's heading for 1. There's no question about that. It will eventually get to 1. But you see, it's actually between the place where it cuts the yellow curve and it cuts the red curve, it's closer to the Weibull distribution than it is to its ultimate limit. Quite a bit closer. And in fact, again, we're out to the 1 part in a billion by the time you get to the point where it's actually closer than the Weibull 0.95. Right? So if you want to find it being better than Weibull 0.99, that's a very large number. 1 part in 10 to the who knows how many. Certainly a place where you'd expect that there's no practical application of probability. So I just want to finish with a summary of the process we've gone through and what we got out of it, assuming we've all done the homework. We start by solving the Cartan equivalence problem. That's done once, and we can use the solution again and again and again. And the only thing that went into that was a non-constant, because we were using log of f as a coordinate, so we can't have a constant f. But a non-constant, twice differentiable function preserved by the action of the affine group on the line. Next, we replaced this originally motivated by samples of size n stability condition by a geometric stability condition. I mean, this is absolutely the natural thing to look at from the point of view of the geometry. Whether it pays off or not from the point of view of probability is something you have to try and see. Right? We did that.
So the first one is powers of f.
Yeah.
And the second is the equivalent class.
Well, the second one is powers of f, but the power can be anything you like now.
Okay.
Presumably any power greater than 1. It's worth thinking about what happens when you start taking square roots. and other roots. For example, in the application to the omega functions, you can take powers less than 1. And you get something useful out of it. But here we just looked at this simplest case. Right? And then the solution of the extreme of the equivalence problem for geometric stability pops out the extreme value attractors. So just as you don't have to know anything about surfaces to find a Gauss curvature, if you know the equivalence calculation, you don't need to know anything about extreme value theory to find the extreme value attractors. They're the exceptional cases, and the equivalence problem churns those out as a matter of fact. And then the second version, we did the same thing. Then finally, we come to this duality between the domains of attraction. And it all boils down to the fact that you have this relation. The relation that's the basis of the equivalence solution, J equals H of I, allows us to identify the differential equation for the distribution and the distribution itself. And that's the key to proving these convergence results. So there's more in the works. We're in the process of applying the same tools to look at the Levy-stable distributions. And that's complicated by the complexity of the parameterizations, which I found a fascinating article that listed the errors over the years in people making the parameterizations of the Levy-stable distributions. Even in one edition of Feller, and the author was not gloating because he included one of his own papers where he'd made a mistake in the parameterization. So I think I have to find Levy's book in the library and go back to the source for that. Anyway, it's also slightly complicated by the fact that you're using complex affine transformations. And so, for example, minus x and x are connected by a perfectly reasonable complex affine transformation. So things are different from that point of view as well. Anyway, that's the end. That's our contact email at ProtonMail if you have any questions, and or maybe you need some hints with the homework. Okay. Oh yeah, I've repeated those sort of landmark papers. The Gdenko one is well, they're all very interesting, and Picklin's did several other papers about this that I still haven't found completely. I'd say, well, if assuming you read French, Gdenko's paper is very interesting. And, right, that's the end. So, any questions? Okay, thanks.